Okay, in section 6 we are going to talk about simplifying radicals. Then we're also going to begin to do operations on radicals, which would be adding, subtracting, multiplying, and eventually will lead to a kind of dividing in the next section. So if you recall, a radical is just a name we give to the nth root of something. We call this the radicand. So that's the number under the root. This is the index of the root. So we can have such the square root of a, we can have the cubic root of b, and so on and so forth. So we're going to try to simplify these radicals, and moreover, radicals that are not perfect. For example, we all know what the square root of 25 is. It's 5. But what is the square root of 50 exactly? Now, of course, we can put it in our calculator, but we want to know how to simplify this radical to something, a simpler form, but still an exact form. So to do this, we're going to have one new rule, a very powerful rule, and this is what's called the product property of radicals. So the product property of radicals says this. It says if a and b are greater than 0, then the square root of a, really the nth root of a, any root, times the nth root of b is simply the nth root of ab. And something very important, this actually works both ways. So you can take 2 and you can multiply it together under the same root, or you can take something that's multiplied together and break it into 2 roots. So going the other way is how we will do what's called simplifying radicals. Simplifying radicals is when we will write a radical with no perfect factors, no perfect root factors. And there are lots of ways to do this. I'm going to show you what I believe to be the easiest way. But what I mean by perfect root factors, let's go back to what we said earlier, square root of 50. Well, square root of 50 has a perfect root factor because the square root of 25 is a perfect square, and 25 is a factor of 50 because 25 times 2 is 50. So this does have a perfect factor, so we will try to simplify that starting below. So we're going to try to simplify these radicals, and we're going to assume all the variables are positive numbers, so we don't have to worry about anything there. So if I look at 18, does 18 have a perfect square factor? So this is where these radical simplifications would go a couple different ways. So the traditional way is think of all the perfect square factors. 4, square root of 4 is 2, square root of 9 is 3, and so on and so forth. And this one does have a perfect square factor of square root of 9. So 18 can be written as the square root of 9 times the square root of 2. And then the square root of 9, of course, is just 3. So this is written as 3 times the square root of 2. So this is the same value as the square root of 18, but it has no perfect square factors. And what it does is it reduces the size of this radicand. So this is what's called simplifying the radical. Now this is the traditional way that this has been done, but I want to show you a little bit different way that I think is a little easier. So I'm going to start with an 18, which is our radicand in our original radical. And what I'm going to do is I'm going to factor this, just factor it like a tree, like you've always done. So 18, any two numbers that multiply 18 we can write in this factor tree. So let's say 6 and 3. And I will circle 3 because it is a prime number. And then 6 can break down to 3 times 2, and these are both prime numbers. So an easy way to simplify this is, since this is a square root is 2, I look for anything that has a matching pair. Are there any groups of 2 in my factor tree? Well, there are 2 3s. And only 1 2. So anything that has a pair, or a perfect, if it's a cube root you're looking for 3, a fourth root you're looking for 2, anything that has the matching group, you put on the outside of the radical. So 3 would go on the outside because there's 2 of them. and anything that doesn't stays inside. So it's the same thing, you just don't have to memorize all the perfect square powers, which I think is much easier to do. You just factor it, look for your groups, and go on. So let's look at 288, kind of a bigger number. So I don't know much that divides into 288, but I know it's even. So I can break it down as a 2 times a 144. 144 is still even, so I can break that down as 2 times 72. 72 is still even, so I can break that down as 2 and 36. 36 is 6 and 6, which is still not prime. But these are 2 and 3, 2 and 3. So a much larger factorization in this case. So now what I want to do is I want to look for any pairs of perfect primes. So I got a pair of 2's here, I got a pair of 2's here, and a pair of 3's here. So the only thing that doesn't really match is we have an extra 2. We have 5 2's, but we're looking for groups of 2 because it's a square root. Always look at this index. It's just nothing there means square. So now we have 2 2's and a 3 that will be outside of our radical. So we have a 2, and a 3, because those are all in blue and have been taken out of the radical. And then 1 2 left in the radical. You can just simply simplify this. 2 times 2 times 3 is 12 square root of 2, or 12 radical 2. Okay, let's look at this one. The only difference really in this one is we have a 5 out in front. So when we do our radical simplification, we will remember there's a 5 to start with here. So 54, if I factor it, I know that's 9 and 6. 6 is 3 and 2. And 9 is 3 and 3. So if I look at any pairs in this radical, or in this factorization, the only pair I have is 3. So I'll put a 3 on the outside from this pair. And then I have a 3 and a 2 by themselves that are left, so I'll keep those inside. So 3 times 5 is 15. 3 times 2 is 6. So this is 15 root 6. So the 5 was just kind of out there to begin with, so we just kind of kept it there. Okay, let's look at this last one on this row. The cubic root of 54, x to the 4th. So a couple of things. We have a variable. And we also have a new index. We have an index of 3. The only difference is going to be when we look at our factor tree, we're going to look for a group of 3 of something. So 54 is 9 times 6, 3 times 3, and 3 times 2. So since we're looking for a perfect group of 3 in this case, there are 3 3's. And then, of course, 1 2 that doesn't match. So just looking at the numeric part of this, this would be the cubic root. So we have the group of 3's, so the 3 goes outside, and the 2 stays inside. I'm going to erase that 3 and move it over a little bit because we'll have to deal with this variable too. So now the variable x to the 4th, we really do the same thing. So we can write it out. If you think of x to the 4th, it's x times x times x times x, 4 of them. So I'm looking for any groups of 3. Well, there are 3 x's. So any group goes outside. So this group of 3 will become 1x on the outside. And then we have 1 left on the inside that doesn't match up. So it just stays on the inside. So it's really the same thing over and over. Anything that matches up comes out. Anything that doesn't stays in. Variable, number, doesn't matter. Okay, let's look at this one. So the number is 25. So we know 25 is 5 and 5. So really the square root of 25 is just 5. So that all comes out of the root. So anything that's left in the root would just be variables. So a to the 4th, if I think of a to the 4th, and I want groups of 2 of it, I could just think of how many groups of 2 are there in a to the 4th? Well, there's 2 groups of 2. And if I look at b to the 9th, how many groups of 2 would there be? If I wrote all the b9's out, b, 9 times, how many groups of 2 would there be? Well, I can make 4 groups of b, squared, 4 groups of 2, and I'd have 1 left over. So just kind of using a little logical thought, we can simplify these pretty easily. Let's look at this one. We have the square root of x to the 7th, y to the 8th, z to the 9th. So no numbers here, all variables. So let's think about x. How many groups of 2 are there in x to the 7th? Well, there are 3 groups of 2 with 1 left over. Y to the 8th. How many groups of 2 are there in y to the 8th? Well, there are 4. And there are none left over. So again, anything that's in even groups comes out, anything that's not stays in. Z to the 9th, how many groups of 2 are there? Well, there are 4 groups of 2, and there are 1 left over. So variables in a lot of ways are easier than numbers because you really don't have to do the factor tree. You just think about how many groups there are, that groups come out, and anything that doesn't just stays in. Okay, let's look at the last one on this page. It is a 4th root of 32, a to the 9th, b to the 20th. So first let's factor the number, 32. I know that's 2 and 16. I know that's 2 and 8. I know that's 2 and 4. And I know that's 2 and 2. So when I'm simplifying my 4th root, I'm looking for any perfect groups of 4. Well, I have 4 2's. So the group of 4 2's will come outside of the radical and be out front. I also have this leftover 2 here, so it will stay inside. So the 4th root of 32 is 2 times the 4th root of 2. Now I just have to do the variables. So we have a to the 9th. So how many groups of 4 are there in a to the 9th? If I wrote out all the 9's in a row, there would be 2 groups of 4, and there would be 1 left. And then finally we have the b's. If I wrote out 20 b's in a row, how many groups of 4 would there be? Well, there would be 5 groups of b, and there'd be no b's left over because the 4 would work out perfectly. So this radical simplified is 2a squared b5 times the 4th root of 2a. Okay, we have some more radicals on this side. We have simplify these radicals here. So we have the square root of 81y to the 5th. So 81 actually is this perfect root, but we can break it down kind of the same way we did before. 9 and 9, 3 and 3, 3 and 3. So we have 4 3's in this root. And since it's a square root, we're looking for groups of 2, so there's 1, 2 groups of 3. So in this radical, I will have 2 3's on the outside, and as you notice, there's no numbers left on the inside. As for the variables, we have y to the 5th. So how many groups of 2 are there in y to the 5th? Well, there are 2 groups of 2 in y to the 5th, and there's 1 left over. So if I multiply those numbers out front, 3 times 3 is 9. We have the y squared, and then we have the y left inside. Okay, let's look at this one. The cubic root of 24, a9, b4. So I'll first start with my number, 24. It's 2 and 12. It's 2 and 6. It's 3 and 2. Since it is a cubic root, we're looking for any group of 3 things. Well, I have 3 2's, and that is the only groups of 3 I have, and then I have the 3. So the 2 comes out because there's a perfect group of those, and then the 3 stays in. And now, same thing with the variables, we're just looking for groups of 3. So if you have a to the 9th, how many groups of 3 in a to the 9th? Well, there are 3 groups of a and nothing left. For b to the 4th, how many groups of 3? Well, there'd be 1 group of 3 with 1 left over. Alright, let's try one more of these and then we'll move on to some operations on these. So we have the 4th root of 32z to the 7th. So if I take 32 I know that's 8 and 4. That's 2 and 2. This is 2 and 4, 2 and 2. So we have 5 2s. We're looking for a group of 4, so I can take 4 2s and have 1 left over. So this is a 2 on the outside and a 2 on the inside. So now we're going to look at the variables. We have z to the 7th. So how many groups of 4 are there in z to the 7th? Well, there's only one group of 4, so I put only one z on the outside. But there are 3 left. So I have z cubed. Simplifying radicals is always a good thing to know how to do. Something we'll use in almost every problem when we're simplifying radicals. Okay, so now we can use our product rule the other way, where we're just simply multiplying radicals. So if we look at the first one, what is the square root of 3 times the square root of 5? Well, since they're both square roots, I can multiply them. This just becomes the square root of 15. I should try to simplify this radical, but 15 is just simply 3 and 5, and those are both prime. So there are no groups of 2 to take out. So this would be it. Okay, let's look at this next example. We have the square root of 6 times the square root of 21. So the square root of 6 times the square root of 21 is obviously the square root of 126. But we want to try to simplify that. So if we do so, we'll take 126 and start breaking it down. Well, I can make it really easy, knowing that 6 and 21. This is 3 and 2, which are prime. And this is 3 and 7, which are prime. So the only group that matches of 2 is there are 2 3s. So the 2 3s would come out to be 1 3 on the outside of the root. Any group comes outside, and anything that's left stays on the inside. So the 2 and 7 multiplied together would stay on the inside. So this is 3 radical 14. Okay, same idea on this one. When you're multiplying the radicands, square root of 8x cubed times 6x is going to be the square root of 48x to the 4th. So now if I break down 48, and remember I'm looking for groups of 2, I could say it's 4 and 12, or I could have used 8 and 6 since I knew that one. 2 and 2, 2 and 6, 3 and 2. So the perfect groups of 2 in this case, well, I see I have 2 2s, and then I have another 2 2s and a 3 on the inside, pardon me. So my radical simplified is I have 2 2s on the outside, they both came out. And then for the variable at x to the 4th, so how many groups of 2 in x to the 4th? There are 2 groups of 2 in x to the 4th. And I almost forgot, don't forget this 3 that I had left over has to stay inside there. So my simplified radical would be 4 x squared times the square root of 3. Okay, a couple more. So the next one, we have 12 times radical 12xy cubed times 3 radical 30x squared y with these square roots. So if I multiply them, I can multiply the radicals, but I can also just multiply these numbers out in front, which are 6. 12 times 30 is 360. I have x and x squared, so I add the exponents, I get x cubed. Y cubed and y to the first is y to the 4th. So I have this big radical that I have to simplify. So I'll start with 360. I know it's 36 and 10. This is 5 and 2, which are both prime. This is 6 and 6. 3 and 2. 3 and 2. So if I look at perfect groups, well, I have 2 2s, and I have 2 3s, and then I have an extra 2 and an extra 5. So numerically wise, I have the 6 that was already there. I take a group of 3 out, a group of 2 out, and inside I have the 5 and 2 still. And we'll simplify those numbers here in just a second. So on the variable part, x cubed, how many groups of 2 are in there in x to the 3rd? Well, there's only one group of 2, so we'll just put x. and there's 1 left over. So if you have 3, you have 1 group of 2, 1 left over. And for the y's, there's 2 groups of 2 and nothing left over. So now if I just clean this up, 6 times 3 times 2 is 36. Xy squared, radical 10x. So again, these problems can look pretty daunting, but if you just multiply them and do these factor trees, it really is nothing to it. So let's do one cubic root example. So we have the cubic root of 16m squared n4 times the cubic root of 40mn. So if I multiply this, I get the cubic root of 640 m cubed n5. So first I'll break down 640, which I know is 64 and 10, 5 and 2. This is 8 and 8, 4 and 2, 4 and 2, 2 and 2, 2 and 2. So a lot of numbers in this one. So now I'm looking for perfect groups of 3, so I need 3 things to match. Well, I have 3 2's right there, so there's 1. And then I have another 3 2's right there. So I do not have anything else. I have this 5 and 2, but they don't have anything to match it with. So when I simplify my cube root, I have 2 groups of 2, 2 groups of 3 2's that come out. Now for the m's, I have m3. So how many groups of 3 are there in 3? Well, there's 1, none left over. Let me put my 5 and 2 that I have left over from here. Then n5, I have 1 group of 3, and then I'd have 2 left over. So cleaning up the numbers, 4 mn cubic root of 10 n squared. So we learned a little bit about simplifying radicals and multiplying radicals. In part 1 of section 3.6, we will have a second video on the second part of 3.6, which is on adding radicals.